Ladies and gentlemen, I'm happy and glad to be here to give the opening talk at this conference in Catania, where Ettore Majorana was born. And I thank the organizers, especially Clementina Godi and Francesco Capuzzello, for giving me this possibility. I was also born nearby, about 30 kilometers from here. So it's I'm particularly glad for this opportunity. So my talk is about some open problems in neutrino physics today. So we have some answer questions even today in neutrino physics. One is what is the absolute mass scale of neutrinos. Two is how many, whether neutrinos are Dirac or Majorana particles. And three, how many neutrino species are there. And all of these are contained in older papers by Fermi, Majorana, and Pontecorvo. So an answer to the first question can be obtained by the measurements of the endpoint on the electron spectrum of single beta decay. This is in fact the original idea of Fermi in his original articles. As you can see there on the left-hand side, there is the end spectrum with the mass of the neutrinos. The article is in German because at the time German was the main language in science. And on the right-hand side, there is a figure taken from the Catania collaboration on the end spectrum. Another possibility is the measurement of the endpoint of the spectrum of single electron capture, where again you can see the spectrum there, and on the right-hand side you see what is the modification to the spectrum if the mass of the electron is not zero, if the mass of the neutrino is not zero. So the problem is that unfortunately the limits on the current values of the neutrino mass are very, very small, of the order of milli-electron volt. So it is going to be extremely difficult with either of these two experiments to measure the neutrino mass. The figures here are, as you can see, with the masses of about 2 to 5 electron volts, but we are now thinking of milli-electron volts, so very difficult to do these measurements. To the third question, an answer perhaps could be obtained with the new program at the Fermi Lab, studying the short baseline, in the short baseline neutrino program, where this is a part of a larger program trying to look for sterile neutrinos, and so perhaps there we could see the possibility whether there are additional neutrinos. These will probably be discussed later on, all these three different possibilities, but now I would like to concentrate instead on the fact that an answer to all three questions can be obtained from neutrinoless double beta decay and the related processes. Neutrinoless double beta decay is the process in which a nucleus X decays in the nucleus Y with the emission of 2 electrons and no neutrinos. So here is a simple sketch of double beta decay in which nucleus germanium 76 decays into selenium 76 by double beta decay, and this process can occur with the emission of 2 electrons or positrons and some other particles. For neutrinoless double beta decay, we have no additional particles, and just decay into a nucleus Y plus 2 electrons or positrons. The half-life for this process can be, for all processes in fact, not allowed by the standard model, can be factorized in the part which depends on the atomic physics, the phase space factors, a part which is the nuclear matrix elements, and the part which is all the physics beyond the standard model. So calculation of these is rather complicated because it involves physics at 3 different scales: atomic physics, nuclear physics, and particle physics. There have been several calculations now of this process, but also let me mention briefly that the case on which 2 electrons and 2 neutrinos are emitted, the half-life can be factorized as a product of a phase space factor and the term which depend on the nuclear matrix element. In this case, the factorization is not exact, but is a good approximation. But for all this process, we need to, in order to extract the physics beyond the standard model, we need to calculate the phase space factors and the nuclear matrix elements. So phase space factors were calculated already in the 1980s. They are contained in books, but we have recently recalculated the phase space factors with exact Dirac wave functions and including also electron screening from the electron cloud. They are available from Jenny Kotila at the University of Iachello, and they are also on the web page of nuclear theory at Yale University. So nuclear matrix element can be written as in the following form. I will put in front the value of the axial vector coupling constant GA multiplied by some matrix element, which here have a contribution from Gamow-Teller, from Fermi, and from tensor contributions. There are several methods that have been used to evaluate the matrix elements, starting from the quasi-particle random phase approximations, the shell model, interacting boson model, densital functional theory. So most of the calculation have concentrated on two processes. One is the emission and reabsorption of a light neutrino with mass much less than kV. And then another process is the emission and reabsorptions of any neutrinos with masses greater than GeV. And so the difference between these two is the part which depends on the physics beyond the standard model. In the first case, this factor F is proportional to the average neutrino mass. In this case, it is proportional to the inverse average mass. Where this is mass of heavy neutrino, which here is indicated by nu h. The other difference is that the so-called neutrino potential for these two cases is different. This is a long-range interaction here. It's like a long-range interaction. The neutrino is massless here, can be emitted at this point and reabsorbed at this other point if it is its own antiparticle. So this will imply that the neutrino is a Majorana particle in order for this to occur. And the so-called neutrino potential has this form. As you can see, this is like a Coulomb-like interaction because in the Coulomb-like, this will be 1 over p squared, which is the Fourier transform of the Coulomb interaction. So this is long range. This is a short range. So the neutrino potential is a constant, which is just the Fourier transform of a delta function. Okay. So here are the most recent results of some of the calculations for the neutrinoless double beta decay, the nuclear matrix element. And there is, as you can see, quite a spread in this matrix element. This is for the heavy neutrino exchange. Sorry, this business with this is really. So this is the result for the most recent result for a light neutrino exchange between different models. And as you can see, there is quite a difference in the spread. Typically, the shell model results are lower than the IBM2 and the QRPA results, which are instead somewhat in more closer correspondence. The next transparency is the case of the heavy neutrino exchange, where also there is a similar story. The results in the previous slides have been obtained with the GA equal the free value, but it is very well known from single beta decay and from two neutrino double beta decay that the GA is renormalized in nuclei. And there are two reasons: limited model space in which the calculations are done, and the omission of non-nucleonic degrees of freedom. This problem of the quenching of GA was very well studied in the 1960s and 70s, but for some reason was later forgotten, and only recent times has been brought up again. So there are two reasons for quenching of GA in double beta decay, which are here indicated with a simple sketch. The first reason is the omission of non-nucleonic degrees of freedom. For example, the delta or some of the other resonances of the nucleons. And this produces a quenching factor of the order of 0.7. The second is the limited model space, which means that we are missing some of the excitations of the nucleus, and this will produce another quenching factor about 0.7. And therefore, we have maximal quenching, which is the product of the two, which is about 0.5. The value of the axial vector coupling constant effective in nuclei can be extracted from 2 neutrino double beta decay, and here is an extraction of this from experiment for two different models, the interacting boson model and the shell model. And as you can see, the quenching observed in 2 neutrinos double beta decay is quite large. GA is quenched to the order of 0.6, 0.5 for these processes. GA has also been extracted from single beta decay in QRPA and will be discussed in detail in one of the talks later on. And again, there one finds values which are as large as the one that I have indicated there. So this question of the quenching of GA has a tremendous impact on neutrinoless double beta decay, because the nuclear matrix elements are multiplied by GA squared, and the half-life then contains the 4th power of GA. So if GA is quenched, that means that the half-life is going to be larger than the one calculated with the value of GA, the free value. In fact, if GA is maximally quenched, then this is a multiplication of a factor of 6 to 30 to have a realistic estimate of the expected half-life. Now, this question is, of course, because it's of great experimental importance, is of much debate at the moment. The two processes, 2 neutrinos and 0 neutrinos, differ from the fact that in 0 neutrino, the virtual neutrino momentum is of the order of 100 MeV, while in 2 neutrino decay, it is just a few MeV. And therefore, the sort of agreement at the moment seems to be that in view of this, perhaps both factors contribute to 2 neutrinos, while only the missing of the non-nucleonic degrees of freedom contributes to the 0 neutrino. Think that the difference in mass between the delta and the proton is about 300 MeV, so the virtual neutrino momentum is below that 200 MeV, but the average value of the excitation is about 10 MeV, so the virtual neutrino momentum in 0 neutrino is above that, and therefore this will not contribute because all the strength will be taken into account. So this problem is currently being addressed from various sides experimentally, and again, some of these experiments will be presented here with the helium-3T reactions, and theoretically by using effective field theory or other ways to estimate that. Now, I would like to mention here that very recently an experimental program called NUMEN has been set up at the Laboratorio Nazionale del Sud here in Catania to measure both single and double charge exchange reaction intensities with heavy ion. And this program will provide useful information on the Fermi and gamma octet matrix elements of interest both in 0 neutrino and in 2 neutrino decay. Francesco Capuzzello and Clementina Godi are the leaders of this experimental program. So the conclusion then of this part is major progress has been made in the last few years to narrow down the predictions of 0 neutrino double beta decay to realistic values in non-nuclear interest. And here are the current limits on the neutrino mass from 0 neutrino, assuming the free value of GA, taking the IBM2 matrix element and the phase space factors of Cotila. And as you can see, here is the so-called Vissani plot, in which the average neutrino mass is plotted against the lightest neutrino mass in electron volts. And there are the various experiments denoted here, and here are the references to those experiments. So the current best limit, assuming the free value of GA, is about 0.85 electron volts, so 85 milli-electron volts, very small. But the remaining question is, what is the value of GA? And there are three scenarios that are possible. One is that is the free value, 1.69. One is the so-called quark value, which in my present opinion is probably the most likely value. And the three is this maximal quenching that is observed in single beta decay and in double beta decay with emission of 2 neutrinos. And this transparency, this slide is of great importance for the experimentalist, because it will set up essentially what is that we can measure in the immediate future. So if GA is renormalized to those values, then as you can see here, it's going to be extremely difficult even to reach the inverted region, because this is the value. This is just the EXO 136 decay. You see that this is with GA 1.69, here is with GA equal 1, and here is with the GA at 0.5. Now, what are the possibilities to escape this conclusion? One is that the neutrino masses are degenerate and large. But this possibility is in tension with some recent result from cosmology from Planck on the sum of neutrino masses. The cosmology can determine the sum of the masses, and the current limit, which is 230 milli-electron volts, then when translated into the lightest neutrino mass, taking that to be 1/3 of that value, is here. So this region is excluded by the cosmological bound. It is true that the cosmological bound is somewhat model dependent, but nonetheless is something that we have to take into account. So this possibility may not be the right one. The next other possibility is other scenarios like Majorana emission or sterile neutrinos need to be considered. So in particular, sterile neutrinos, which are at the moment the subject of many discussions. Sterile here means neutrino which has no standard model interaction, as was introduced by Bruno Pontecorvo already many years ago. Other possibility is that there are other non-standard mechanisms contribute. And we have recently studied all mechanisms, both short range and long range of dimension 6 and dimension 9. And I may say something if I have time. So there are other possible. Now, sterile neutrinos. For sterile neutrinos, we have already, several people have already done the calculations. The question whether they exist is going to be determined both at experiments at Fermilab, whereas you know they're assembling 3 different detectors, one very short range, very close to the accelerators, about 20 meters, one about 200 meters, and then Icarus is going to be put at about 1 kilometer distance, so that might be a way to detect these sterile neutrinos. But the only difference in the calculation is that the function f that you saw there at the very beginning, now for sterile neutrinos will be written in this form, and also the potential will change because now the neutrino will have a mass which may be comparable to the momentum, to the Fermi momentum in the nucleus, and so this has to be modified. So there are several types of neutrinos, as you know, that have been suggested. One is the sterile neutrinos heavy sterile neutrinos with masses much greater than 1 electron volt. There are light sterile neutrinos with masses of the order of 1 electron volt. This, I suspect, is going to be discussed later on during the week, and just here mentioning that these are masses of the order of 1 electron volts. Now, then one can work out a super formula in which all neutrinos are put in. There are the known neutrinos here, unknown light sterile neutrinos here, electron volt scale of keV square. Here this unknown heavy sterile neutrinos and unknown heavy neutrinos. And the matrix elements have been computed. And here I'm going only to show the result to say that if sterile neutrinos are present, then this will change completely the picture. And so this is the picture that one obtains with sterile neutrinos with the properties that Giunti and Laveder suggested. And you can see now that the inverted region extends much further up, and also the normal region. And in fact, if we put in here the current experimental limits, we see that already Kamelan-Zend is already at the verge of being able to exclude sterile neutrinos with that mass. But this figure is prepared with the free value of the axial vector coupling constant. If that changes, of course, these people would change. And in any event, I think that this is reachable with Gerda phase 2, and with the quark probably we will be able to reach and to exclude some of these sterile neutrinos contributions. So finally, to complete these lectures, I would like to briefly mention what we are doing at the moment, which is that of looking at the non-standard mechanism and for neutrinoless double beta decay. In particular, we have been involved in looking at the short-range mechanism using this form of the Lagrangian, which contains several terms. This was supposed to be presented here by Lucas Graf, but unfortunately, I think he will not come, and so will not be presented. So let me say a few words. So this is all dimension 9 interactions. As you can see, there is 3 currents are present there. This, which is dimension 6, was already studied by Ali and others a few years ago, and include both scalar and pseudoscalar interactions, vector and axial vector. Of course, the one that we already calculated is V minus A, and then tensor and pseudo tensor. And to conclude in time this presentation, so no matter what the mechanism of neutrinoless double beta decay is, its observation will answer these fundamental questions that were posed at the very beginning. What is the absolute neutrino mass scale? Whether the neutrinos are Dirac or Majorana particles, and how many neutrino species are there. Indeed, my present view is that if observed, neutrinoless double beta decay may also provide evidence for physics beyond the standard model other than the mass mechanism. And therefore, even if at the moment the fact that the neutrino seems to have such a very small mass in the mass mechanism is worrying many people, still I think the experiments are worthwhile doing, and the search is worthwhile continuing, because it may be that there is some additional mechanism to the mass that is present there, and which will produce mass of the order of 100 or 150 milli-electron volt neutrinos. And conversely, if this will not be observed, then this will set stringent limits on other possible scenarios, like the occurrence of sterile neutrinos or the occurrence of additional mechanisms. And with this, I would like to conclude my presentation. Thank you for your attention. I'm sorry that at the very beginning there was this problem with the slides, but I hope that at least you have followed what I've said, especially in the last part, which is my main message. Thank you very much.